Please note that this is a sponsored event and any opinions expressed are those of the presenters and do not necessarily reflect the views of ASCE. ASCE also asks that presenters and participants refrain from discussions surrounding competitors and pricings of products and services. And now, without further delay, welcome to From Traditional to Innovative, EPA NESHAP, Alternative Work Practice and the Future of Asbestos Pipeline Replacement, sponsored by Azuria Water Solutions. With us today, we have Andrew Costa, Vice President I'm sorry about that, Vice President of Sales and Strategy for CTPS and Pressure at In Situ Form Technologies. Welcome, and over to you, Mr. Costa.
All right. Thanks so much, Robin, and thanks everybody for attending today. I really appreciate you carving out a little bit of time for us. Again, my name is Andrew Costa. I'm the VP of Sales and Strategy for Azuria Water Solutions, focusing specifically on CTPS, one of the technologies we're going to talk a lot about today, and in pressure pipe in general. So I have a lot to cover today. Again, thank you so much for joining us. Let's go ahead and get going. Just a little bit of background for you real quick about In Situ Form and about Azuria, just in case you're not too familiar with our company. We started off back in the early 70s as In Situ Form. We are the creators and pioneers of the CIPP process. We're global leaders in the trenchless space. We do things in gravity and in pressure. We do assessments. We do all kinds of renovation type work, and we've really diversified over the years. We are a vertically integrated company. We have a number of different technologies that we handle from start to finish, particularly with CIPP. We handle the manufacturing, wet out, and installation. Those are all certified processes that we control on the supply chain. Corporate structure-wise, we are Azuria, right? That's our parent company. We are a private equity-owned company that is growing like crazy. We've acquired about 25 companies over the last 3 or 4 years, and we've grown our revenues to be a little bit over $1 billion company. So we are rapidly growing and rapidly increasing and changing the face of the company. We do a lot of stuff these days, so most people know us as the CIPP company. Still true. We also offer a lot of different services, whether that's in the pressure space or gravity, from Primus line FFRP lining to installations with fusible PVC like pipe bursting or directional drilling. We do clean and CCTV. We do manhole rehab. We do laterals. Today, we're talking about close tolerance pipe slurrification for asbestos cement remediation and a lot of the environmental regulations that go along with that. So I want to give you a lot of background today. There's a lot going on when you're dealing with asbestos cement. We're dealing with regulated materials. So we'll talk through some of that regulation. We'll talk through some of the terminology because it's really important to have that foundation. We're going to go through some of the traditional remediation solutions from the rehab and the replacement side. We'll go through a little bit of history and kind of the lead up as to how this technology came to be, what it is, how it works, and then we'll talk through some real world applications on a current project that we're working on.
Hey, Andrew.
Yes.
I don't see your slides.
Oh, I'm so sorry. Let me share. Can you see my? Oop, nope, hang on.
Almost.
Hang on.
There we go.
Can you see that now?
Yes, we can.
Okay. Thank you so much I appreciate the talk. Okay. So let's go through some background of asbestos cement pipe, or just asbestos in general. A lot of people aren't really aware that asbestos is a naturally occurring mineral used to strengthen building materials. It's been around a really long time. Humans on this planet, I'm not sure about aliens, but humans have been using asbestos about 5,000 plus years. So it's been around for a really long time. There was a big increase during the Industrial Revolution. As we started ramping up with a lot of buildings, and during that time, we really started increasing the use of asbestos as a building product. Around the late 1800s and early 1900s, we started noticing that it sort of had some negative health benefits or negative health things associated with it. So we started figuring it out back then. But as its use started to continue and ramp up, it was kind of at its peak that we really started fully understanding and studying exactly the negative health aspects of asbestos. So kind of as it peaked, that's when we really started regulating it. If you grew up kind of around the time that I did, these are very familiar terms as it pertains to asbestos. So asbestosis, mesothelioma, and lung cancer, these are all major health consequences that are direct consequences of asbestos fiber exposure, some of which is short-term exposure and some of which is prolonged exposure over the period of several years. So some pretty negative health consequences associated with the material. Most people these days kind of have a very strong connotation with asbestos being a concerning material. The challenge here for us on the infrastructure side is that about 15 to 18% of our pipelines in the US and Canada are made out of asbestos cement. So that represents over 600,000 miles in North America. And with about a 50 to 60, 70-year-old engineered design life, these pipes were, again, a lot of installations during the Industrial Revolution. So when you start getting into infrastructure building in the 50s, 60s, and 70s, with a 50 to 70-year engineered design lifespan, like we're there right now. And a lot of these pipes are far past their useful life. Some are in very good shape, but most are kind of nearing the end of that life. Traditionally, up to this point, we've historically handled asbestos cement pipe by either the replacement method or by abandoning these pipes and rerouting a new line. But because of the health risks that we talked about and a lot of environmental regulation out there, we've got a lot of inventory still in the ground. There's a huge need for the improvement in how we remediate our AC pipes. Just like Azuria's thesis, as far as trenchless technologies, we're trying to sort of infuse this trenchless concept into a historically dig and replace history. So from the regulation side, there are a lot of regulation that comes with asbestos and asbestos cement. From the federal side, you have the EPA, and as an extension of the EPA, you have NESHAP, and we'll talk about them in a minute. We have the Department of Transportation involved when we are moving these materials from one point to another. And then obviously when we're dealing with worker safety and workplace safety, we're dealing with OSHA. The EPA delegates the authority of asbestos governance and legislation to the states. And from there, what the states do with it is a little bit different depending on which state you're talking about. A lot of states will just sort of take that delegation from the EPA as is. They don't make any changes and they just sort of go about their business regulating the material. They do that through groups like DEQs and DEPs. There are a lot of different spins on kind of what environmental legislation governs asbestos and the implementation of NESHAP. So some states just take that delegation and they run with it. Others add on layer upon layer upon layer of additional things that mount as far as the regulation goes that are there to deal with. So some important terms to know. We talked about NESHAP. So NESHAP is the National Emission Standards for Hazardous Air Pollutants. This is the regulatory agency that manages and regulates air quality, as specifically with asbestos. If you think back to where asbestos was primarily an issue, it was in vertical buildings and structures. So primarily it's governed as an airborne or an air quality issue. Again, this is managed by the US EPA under the NESHAP. Sorry? Asbestos containing material is anything that contains more than 1% of asbestos. So it doesn't matter what it is, if it's a pipe or if it's a roofing shingle or whatever it is, if it has more than 1% of asbestos, we call it an asbestos containing material. Once you start messing with asbestos containing materials, so you can sand it or cut it or crush it or abrade it, pulverize it, whatever you want to do to it, once you start doing that to asbestos cement material, it makes it friable and it makes it regulated. So even if it's not friable, once you start messing with it, it becomes a regulated material. That's very important because as soon as we start doing anything to our infrastructure, this becomes a regulated material that we're talking about and it becomes subject to all of the different conditions of the NESHAP. So let's talk about that real quick. NESHAP categorizes asbestos into two categories, and I don't want to spend too much time here, but I want to differentiate the two. So category one, these are non-friable materials that are pretty resistant to damage, right? These are low risk as far as fiber release. These are things like floor tiles and roofing products and gaskets and things like that. Most of what we're dealing with on the underground utility side is category two. These are non-friable materials if you don't mess with them, but they have a higher potential to become friable and release fibers once we start doing construction activities to them. So these are things like transite siding, shingles, wallboard, and for us, asbestos cement pipe materials. So the NESHAP has very strict work practices when it comes to minimizing or preventing the release of asbestos cement fibers. And that doesn't matter if you're talking about category 1 or category 2. So anything that has been fractured or broken, NESHAP, especially if it's category 2, NESHAP calls that regulated asbestos cement material, or they call it RACM. And again, it's regulated under the asbestos NESHAP. If it has two things, if it becomes friable, it's regulated, but it's got to be over 260 linear feet. And I think that's generally within a calendar year. So if you're just remediating a 5-foot section of a pipe for a point repair, that's not going to fall under the regulations of NESHAP. You've got to have worker place safety because you're dealing with hazardous materials. But as it pertains to NESHAP, once we get above 260 linear feet, that's where these regulations kick in. So if you kind of want to understand, like, is this material regulated or not? Is it friable? Yeah. Is it over 260 feet? Yeah. It's regulated, right? We call that regulated asbestos cement material, or RACM. Okay, what do we do about it, right? Let's talk about what the EPA has approved as far as solutions for remediating AC pipes. On the rehab side, these are trenchless methods. These are EPA approved. We can do CIPP, we can do slip lining, or we can do spray applied pipe. These are partially not disturbed because we're not messing with the majority of this line. We partially remove the ends where we have excavations, but these are trenchless technologies. These are things that the EPA very much likes. On the replacement side, there's kind of two things, and they both involve replacement. You can have direct replacement, which is open cut construction, right? The EPA approves this. The pipes are completely removed by snap cutting, so not saw cutting, but snap cutting. Or in a variety of states, not all of them, but in many states, you can abandon this pipe in place. That pipe is not disturbed. It just leaves that pipe still in the ground. It's not preferred, but it's approved. So on the direct replacement side, there's a lot of things that come with open cut construction. And this is kind of the value proposition of trenchless versus open cut. It's very disruptive. It tends to be expensive. It does take a lot longer than trenchless technologies. There are a lot of social costs that go with this and a lot of restoration. These are all kind of fundamentals to kind of getting away from that direct replacement type of mentality. On the grout and abandon side of things, again, tends to be time consuming and costly. It does leave the asbestos in the ground, which is non-preferred. You're dealing with potential conflicts wherever you're going to lay the new line. Oftentimes, if you're moving that line several feet away or across the street, you're dealing with new permitting, new easement acquisitions. These are things that add to the process. They add engineering fees and time. The environmental results are not ideal. And if you grout fill and abandon asbestos cement pipe, that's okay for now, but what happens in the future if you need to make some modifications to that area? What if utilities need to be changed or removed or moved? What if that neighborhood grows? There are always changes that we're experiencing. If you now need to cut that area, you can't snap cut it anymore. You're saw cutting through a solid piece of pipe. That is something that is a very dangerous process that will release a ton of fibers in the air. So in essence, it just kind of takes the problem and it shifts it down the line. So we're going to talk a lot about this CTPS process, and I want to give you a little bit of backstory as to kind of how it came to be. And it's got some roots in trenchless technology from the pipe bursting community. And the pipe bursting community had been seeking some assistance from the EPA for a number of years through what they were going to call an alternative work practice. And they needed some altercations or some release from the NESHAP requirements because the process didn't meet all the requirements to the letter of the law. And because that process had been denied, it's not an approved process right now. And so we were on a project in Greenville, South Carolina. It was a shallow pipe bursting project. It didn't have anything to do with asbestos, but it was kind of the genesis of this close tolerance pipe slurrification, or CTPS process. And it allowed us another opportunity to engage with the EPA on meeting regulations. So this project in Greenville was a 6-inch upsize to 8-inch pipe bursting project of clay pipe. So it was gravity, but it was really shallow. It had a foot, maybe 2 of cover, and the alignment was running underneath slabs and carports, decks, and a lot of things that when you pipe burst in really shallow environments, you're dealing with heave or pipe float. And so with the displacement of that pipe with bursting, this was just too shallow. So we made some modifications to a directional drilling process and we attached a reamer and we ended up just kind of chewing up that clay pipe to avoid creating that heave. And so connect the dots to a process, we sort of said, well, what if we sort of what if we applied this process to asbestos cement and instead of bursting it or breaking it, what if we created a slurry and we ground it up and we moved it out? And that's kind of where CTPS was born. And so we engaged the EPA, and those are sort of the early beginnings of how this process came to light. So let's talk a little about, we call it close tolerance pipe slurrification. Unfortunately, there's not a more smooth version of how to call this thing. That's just what it's called. So we call it CTPS for short. There's a few things that I want you to understand before we dip into what CTPS is. So if you're tuning out or if you're multitasking, I really want you to focus in on a couple key things on this process before we dive into it. Number one, it has federal EPA approval. So it does have this alternative work practice to NESHAP that we had talked about that the other communities didn't have. It does, and this is the only EPA alternative work practice that exists. It's literally the only one. It does have an ASTM standard, and it does have installations in multiple states. So what is it? What is CTPS? CTPS is the only approved, EPA approved trenchless method for replacing asbestos cement pipe. It's a trenchless technology, right? That's what we do. It's actually very simplistic in nature. It uses a lot of very common trenchless ideas and equipment that's been around for a long time. So it uses directional drilling equipment and it uses bentonite drilling mud, very familiar materials in the trenchless space. What it does is it combines the drilling mud and the asbestos, turns them into a slurry, and it pulls it to a pit where it's hauled away and can be disposed of. And what that does is it allows us to remove and eliminate leaving friable asbestos cement pipe in the ground. We can do that for pipelines that are 4 inches in size to 20 inches, and we can upsize at least one size and sometimes two, depending on diameter. So the value proposition for CTPS is very similar to what a typical trenchless value proposition would be. Because remember, we're applying trenchless to a traditionally open cut type world. We are reducing excavations by about 90%, sometimes more in many cases. There is a huge reduction in restoration and in the social cost because it tends to be a faster process. It gets the asbestos out of the ground and it has compliance with EPA and NESHAP regulations. So it's a very environmental friendly process. So from a work sequence side of things, I'm going to walk you through all of this real quick. We have to dig access pits on either side. So I know this is a trenchless technology, but it's not a pitless technology. We're in pressure environments, so we do have to get access to this pipeline. So we're going to dig excavations on either side, and we're going to make very small intermediate excavations at the service connections or at any T's or valves that we come across on the alignment. We're going to use those for relief holes. I'm going to show you an animation of this here in a minute, so it should make a little bit more sense visually. The next thing we do is we push our drill rod from one end to the other. Once that's in place, we start to attach our tooling to it. And I'll show you what that looks like here in a minute. Once that tooling is there, the train is going to spin and it's going to do its thing and start the CTPS process. So here's what the tooling looks like. So here is your bad asbestos cement pipe that we're going to get rid of. The first piece of tooling that we attach is a guide reamer. And this is basically just what it says. It's going to guide our process along with the alignment of the pipe. We stick with and we use the existing alignment. So this will help us keep centered in the pipe. It'll help us follow any jogs in that alignment and help keep us centered. The next piece is really important. This is the back reamer, which is a fancy name for a cutting head. This also will spin. This is where the bentonite drilling fluid will be injected, creating a wet cutting environment. The back end of this, there's a pull head with new fused product pipe on the back of this. This is the new product pipe that's going to be pulled in during the process. So we're going to see an animation, we're going to walk through this. And even though I've explained it in a series of steps, all of this is happening at the exact same time. So it's one continuous process. One of the important things to note is that we're taking a little bit of soil with us during the process. So the term close tolerance, our tooling is sized to where we take about a half an inch of soil around the outside diameter of this pipe. So when we inject our bentonite drilling fluid, we're going to be creating a slurry with the drilling mud, the asbestos cement pipe that we're grinding up, and a little bit of earth. This is going to combine to form a slurry that's going to be kind of pressurized. This environment that we create because of the close tolerance creates some pressure. It helps us pig or kind of squeegee this material from where it's created to the end of the pit, with pulling in the new fused pipe at the exact same time. The cutting head is going to spin at about 240 RPMs, and all this process is going to happen at the same time. So I want to show you an animation of kind of what that looks like. The important thing to note on this process is that the asbestos fragments are encapsulated in the slurry. So all of the material that we're dealing with now is encapsulated, right? That pull head is flat. It's going to force that material like a squeegee or a pig to the end, again, pulling in that new product pipe. Once it gets to that end excavation, it's going to accumulate. Again, it's all encapsulated. The material ends up being like flowable fill. If you're familiar with like low strength grout or flowable fill, that's exactly what the material has the consistency of. There are trace amounts of the material that will be left behind. So the process gets about 98% of the material out. The trace amounts that are left over, and it's a very, very thin amount, will actually harden again to become non-friable and are encapsulated in that skim coat that we've created with the drilling mud. Once that stuff is all into the pit and all of our slurry has been kind of accumulated, we will vacuum it out and we will haul it away and dispose of it just like we would with solid sticks of asbestos cement pipe according to all the federal and state and local material regulations. So I'm going to start an animation for you that hopefully should paint a better picture of what the process looks like. I'm going to jump ahead. There's a lot of words at the beginning of this. So let's dive into the process. So if you remember, we're talking about pressurized pipelines. These are not gravity lines. These are pipelines under pressure. So we have to get access to them. So here's a cutaway of your bad asbestos cement host pipe. We are going to dig 2 excavations, one on either side. Depending on the size of the pipe, we may have a little bit larger excavation than another, but generally about 10 to 15 feet in length. So we do one on either side. Then we take our drill rod from our HDD rig and we're going to push that from one end to the other. Now it's here where we want to start our process. We attach our tooling. So here's our guide reamer. Here's our cutting head. And then here is our pull head with our new fused product pipe. So the end result of this is going to be a brand new pipe. So again, it spins at 240 RPMs. Here's your bentonite drilling mud that's being infused into there. It is going to wet cut and grind up this asbestos. Again, about half an inch of earth along with the asbestos, and the drilling mud will create this slurry that will be pressurized and kind of pigged and pushed from one end to the other, all while pulling in this brand new pipeline with it. So again, once that material is all pushed to the end of the pit, again, it's all encapsulated in our slurry with our drilling mud. We are going to vacuum it out and we are going to haul it away. So it's a very neat and very economic process. Once that process is done, we are going to reconnect our services. We're going to put our pipe back together, chlorinate, disinfect, if it's a water system, and put everything back together again. And you've got a brand new pipe in its place. So it is a replacement technology, again, approved by the EPA. We are getting rid of that asbestos cement host pipe, and we are pulling a new product pipe in its place. So it is a replacement technology. So timeline-wise, remember we said regulation of asbestos started back in the 70s. We're going to jump ahead to 2019 and the alternative work practice that we mentioned. So on that job that we did in the Carolinas, we worked with the EPA and we kind of worked through this process with them. We had a lot of input as to what needed to be done to be in full compliance with the asbestos NESHAP. And so we checked all of the boxes, answered all the questions, solved all the problems that kind of needed to be solved. And in 2019, we were approved for the alternative work practice for CTPS. It is, again, the EPA's only alternative work practice. And in that document, in that alternative work practice, they consider CTPS as a direct equivalent to open cut, dig, and replace. This is in the Federal Register, so there's the number right there. You can look it up. There's a link to this document in the chat. You can go there and kind of see all of the information that's involved with the work practice. It's a very lengthy document. I think it's like 60 pages long. But in that work practice, there's a lot of information, some of which talks about the encapsulation. And so the EPA determined through testing and through working with us that the CTPS process fully encapsulates all of the asbestos fiber. And 98% of that material is getting removed from the ground. So again, they are considering this the only other approved replacement process along with dig and replace. And they consider all of that asbestos cement material to be either removed or encapsulated during the process. Those are very, very important designations that have to be fulfilled in order to get something like an alternative work practice. Fast forward a couple years, and the EPA wanted to issue some guidance. They issued a memo, and it was basically a clarifying memo, and they wanted to outline a handful of things, basically some do's and don'ts as far as what they approved and what they didn't. On the approval side, they wanted to clarify, right? We've got this new process. They want to make it clear and go on record that there are two approved AC pipe replacement methods. One is open cut construction or open trench. Two is our close tolerance pipe slurrification method. They even go along to sort of say, all right, let's talk about what's not approved, right? There's a section in this memo that they call other not approved technologies. And they go ahead and list that pipe bursting and pipe breaking are not approved technologies because they do not comply with the requirements of the asbestos NESHAP. So they felt like they needed to clarify this. So they issued this memo as some guidance to both the federal level and for the adoption at the state level. Fast forward another year, the ASTM for CTPS was worked through and approved. This happened in 2023. And just like an ASTM for any of the other trenchless technologies that are out there, whether it's pipe bursting or CIPP, it's a standard, right? It's a way to standardize and document a lot of the things that are really important and fundamental to the process. There is a lot of redundancy in our ASTM with materials handling and NESHAP requirements. So if you were to read cover to cover the ASTM and read all of NESHAP, and you were to read our alternative work practice, there is a lot of crossover and carryover because there's a lot of that data that's the same and a lot of those processes that carry from one to another because they're all kind of fundamental to making sure that we meet regulations. So there's material testing information in there. There's record keeping information. There's just a lot of guidance as to how you do the CTPS process, do's and don'ts, testing, record keeping, Q&A, things like that. So fast forward again, if you want to see some real world applications, there is a project currently being performed underway in Sunrise, Florida, that's about 38,000 feet of both potable and force main AC pipe, 6-inch, 8-inch, and 10-inch, mostly water, but a little bit of force main. I want to walk you through that job, but first I kind of want to show you what a typical, especially here in Florida, residential CTPS setup looks like, right? Here in Florida, a lot of our neighborhoods are very densely populated. The houses are stacked right on top of each other. So here's kind of what a typical setup looks like. And here's sort of what you're going to see down in Sunrise. This is about a 450-foot span. It's about half the block. So this would be one installation for our CTPS method. So like we talked about, we're going to dig a couple of pits, one at the start of the process and one at the end. And we are going to surgically now just dig at valves and service connections. And we're just going to make very strategic excavations. We can choose most of the time where we put our termination pits, and we can move these to make sure that we're staying in the green space. So in this roughly 400-foot run, if you were to open cut this and replace it exactly where it is, you would be obviously directly open cutting 450 linear feet of pipe. With the CTPS process, we've reduced that by about 90%, and we're only digging in about 40 to 50 linear feet total on this length of run. This would take us about a day. You can see our new fusible PVC that's staged right here. And that process would just start here and it would pull that material all the way to the beginning. And again, this would be about a 1-day job for us. So it kind of helps put into pictures sort of what this process looks like, at least from a typical setup or from an aerial view. So hopefully it kind of speaks to the benefits of the project as it compares to open cut construction. Because if you were to open cut all of this, you've got, let's see, 1, 2, 3, 4, 5, 6 houses in this run. That open cut goes directly over all 6 of these guys' driveways. So now we've got 6 driveways to restore. This alignment sits in the green space, so restoration on the CTPS process is very minimal. There's no sidewalk cutting, there's no road patching, and there's no fixing of everybody's driveways. So the restoration and social costs are quite a distinct comparison to open cut construction. So let's take a look at our City of Sunrise job. Here are some typical pictures of kind of what this job site looks like from a real world perspective. So here is our directional drill rod that's staged right here. So here is one of our pits. This is where the material will collect on this job. But you can see, so pretty minor traffic control. You can see, if you look, you can kind of see some excavations. These are all green space excavations. So there's a driveway here, there's a driveway there, there's a driveway there. We're not digging in any of these driveways. We're not open cutting through this. We might have a little bit of roadway restoration right on the side here of this excavation, but no impact to the sidewalks, no impact to the residents other than they're going to be on temporary water for a couple days. They're going to have some road ramps here as we set up our temporary water. So the inconvenience for these guys is really just backing over a slight road ramp on their driveway. No open cutting through here, no unsightly, restoration efforts that are going to mess with the beautification of their driveway. And we do this strategically. So throughout this neighborhood, we said on a 500-foot run or a 450-foot run, you've got 6 driveways to contend with. That adds up really quickly over a 40,000-foot job. So here's a little bit of a view coming from, there's our drill rod that is staged inside of the asbestos cement pipe. And this is going to be pulling the material. This is where the material will accumulate into this pit. Right now, because this is the beginning of this run, you can still see what we're talking about. After a short amount of time, material will accumulate in this pit and it will start to fill up like you're filling a bathtub with water. If you go down to the other end of the pit, this is the start of what we're talking about. This is where our tooling is set up. This is where we will stage our head that will keep us centered in the pipe. This is our cutting rod. I'm sorry. This is our drill stem right here. This keeps us centered in the pipe. This does all the cutting so that we can stay with that alignment. We attach our new product pipe on there. We can do fused, so fusible HDPE, fusible PVC or fused HDPE, but it has to be fused pipe. And then these are some shots of kind of what it looks like getting that material staged and into place as it goes through the process. And then as that slurry starts to move from where we're creating it, as we grind up that asbestos cement pipe, and as we pull it to that end excavation, that material again starts to flow out. Again, it has the consistency of a flowable fill or that low non-cellular grout. And eventually this pit will fill up with material, and then we will kind of just be working in more of a subaqueous environment of slurry. So as far as what it looks like when you start and what it looks like when you begin, here's kind of what that looks like. Here's the component that keeps us centered in the pipe. Here is our grinding head. And as that moves along through the pipeline, through the alignment, you end up with basically just an excavation full of concrete. That concrete, if you were to go on vacation and come back to it, will set up and reharden and become non-friable, and you will have a giant concrete block inside of that excavation. From a materials handling perspective, that tends to be a good thing, right? We do like to handle the materials right away when they are flowable and they're in a slurry type of a consistency. But depending on the waste disposal group that we're working with, oftentimes they will put that into another containment type of like a bin or a dumpster, and they'll let that material solidify. Oftentimes they will wrap it with plastic and they will bag it and tag it just like we would if we were removing full sticks of pipe. So depending on the location, what that waste management company prefers, and maybe what the ultimate disposal site prefers, There are a number of different options as far as materials handling perspectives, but this is a material that will reharden and become non-friable again. So again, if we were to walk away from this, this will harden back into a giant solid block of concrete. So we mentioned very small excavations. So in a potable water system, we do disconnect those service connections. And at those service connection disconnects, we have very small excavations. We will use some of these as relief holes. With our close tolerance of only a half an inch of soil being taken around that pipe, it does pressurize that environment. It helps us pig or pull that material from where it's being generated to the end. But during that process, we do have little relief holes that we designate. We just sleeve a little piece of pipe down there, and we can use that to vacuum out and kind of help relieve some of that pressure during the alignment. And we will do that, sometimes a couple of times during one of these runs to just alleviate some of the pressure that gets generated during this process. Once all that material accumulates in that end pit, we are going to vacuum it out, haul it away, and dispose of it according to the local regulations. So CTPS has a lot of advantages, right? We talked about the environmental regulation and the compliance side. So we've got full compliance with NESHAP and with EPA regulations. And like we said, we are the only trenchless replacement method that's approved by the EPA. Lots of environmental advantages over non-approved AC pipe replacement methods that make pipe friable and leave it in the ground. Tons of restoration and cost advantages over open cut construction. Remember what we said, we're eliminating or reducing open cut construction by about 90%. That's a huge deal from a disruption side of things, and it really speaks to the trenchless technology thesis of how it differentiates from open cut construction and the disruption that we sort of save from that remove and replace or reroute type of approach that's kind of been done up to date. Because we're using the existing alignment, we're not worrying about new utility easements, so the design and the planning of these jobs tends to be a little bit more simplified. We're not having to acquire new easements. We're not dealing with alignment issues. We are just kind of following the existing alignment of that original pipe. And we're getting that asbestos cement out of the ground. So if you're talking about good, better, best, the EPA does allow you in most places to leave that asbestos cement pipe in the ground if you grout it and abandon it. But obviously the preference as far as good, better, best is to get that material out. Our inventory of AC pipe is in such bad shape these days that some of it, the EPA considers it as a friable material, even though construction activities haven't been performed on it. So we haven't saw cut it, we haven't abraded it, we haven't crushed it, we haven't pulverized it, we haven't done anything to it. Just because of the fact that these pipes are 50, 60, 70 years old, their length of service in that environment has left these pipes in such poor disrepair that the EPA does consider some of those pipes as friable materials, and they want friable materials out of the ground. So to kind of sum up before we get to some questions, again, we mentioned CTPS is the industry's only EPA-approved method for the trenchless replacement of asbestos cement pipe. It's got a lot of advantages, right? We talked about this as far as the differentiator between open cut construction from the restoration side, the efficiency side, from the social costs. There are a ton of benefits of just going trenchless in general over open cut construction, but particularly with the CTPS process as it pertains to the dig and replace method. There are a lot of municipal owners and engineers that are starting to implement CTPS in their AC pipe removal programs as an alternative to dig and replace or rerouting projects. So if you need any information, I highly encourage you to reach out. There'll be some next steps toward the end of the presentation. This process is allowing states and municipal asset owners to remove AC pipe from their system and do it much more efficiently, cost effective, with way less disruption than the open cut and replacement methods. So there's a lot of resources that have been put in the chats. I think there's a link to the animation. There should be the PDF of the alternative work practice, or the link to the alternative work practice site where you can download a few different documents. The actual alternative work practice document is there. There's also an FAQ document that's there that you can download. I think we've got the PDF to the EPA memo is also there. And I think we've also attached a product data sheet or a cut sheet for the process that's there. So I really appreciate you guys joining me. I know there's been some questions that have kind of popped up in the chat. I'd love to hear from you guys right now to see kind of what questions have come up, and then we'll talk about next steps after that.
Yes, so we've had several questions roll in. One of the first ones, how does the slurification cutting head handle existing tap saddles and repair bands?
Yep, so great question. We know that repair clamps are going to come up over time, right? These pipes are in disarray and they've been repaired, right? They've had spot repairs on them over time. As far as service connections goes, or things that have had saddles, we're going to go ahead and dig down on all the service connections before we get going with our process. So we're going to address saddles from the get-go, right with our disconnection of the existing services, and we're going to take those off. When we come to repair clamps, though, those are kind of like stopping points for us to pause, dig down on those real quick, and get rid of those. So unfortunately, we don't have any control over where those are located. We sort of hope that those are not in somebody's driveway, but if they are, there's really not anything that we can do about that. Currently, they really haven't been too big of an issue for us, right? It's very easy for us to just pause the operation. We know when we hit a repair clamp, it's a very obvious type thing that happens. So we stop, we pause, we just dig down on it real quick. We make a very small excavation. We just take that repair clamp out and then we fire back up and we keep on going. So great question. Stuff that we handle very frequently and on a daily basis. Well, maybe not on a daily basis, but on a pretty consistent basis.
All right, the next question. Do previous repairs made on the AC pipe affect CTPS capabilities, specifically when a steel or ductile iron clamp coupling were used?
Yeah, same kind of thing. So we just answered that one. As far as repair clamps goes and previous repairs, once we hit those, we're going to stop, pause, dig down on them, get them out, keep on going.
Right. Do you need to disconnect services before running the new pipe through?
Yes, 100%. That's the first step in our process is we will put those residents in that section on temporary water. We'll disconnect those services, take off any saddles that are there, and start our process. Once that process is done, we'll reconnect services, take them off temp water, and obviously chlorinate, disinfect, just like you would with any type of new product installation. A lot of our methods and material and means as far as new product installation of a brand new pipe that's being laid is very similar, right? We're just getting that new product pipe in trenchlessly.
All right. What is the maximum length between entry and exit pits?
Yeah, great question. I'm not exactly sure how far we can go. It's farther than we generally go on water lines because we tend to be sort of shortened up just by site conditions and the situations of that particular system. In a lot of water systems, there are things that kind of get in our way, like hydrants or T's or valves or things like that. These are what are generally referred to as opportunities for access. So usually our typical installations are around 400 to 500 feet. We can go longer than that. So if you were to get us in an environment where we didn't have those things in our way, maybe we're in a sanitary sewer force main environment where you don't have, those service connections to contend with, and maybe you've got some longer lengths in between runs, we can do several hundred feet longer than what we typically do on a daily basis. So a lot of that just kind of depends on the site conditions of the system that we're working in. And oftentimes we're in pretty densely populated residential areas. And just from a space standpoint, there's only so much space we have to work with. Oftentimes we're kind of relegated to working in that space and only being able to fuse up as much pipe as we can kind of do without taking up too much space and blocking people's driveways and ways of life. So a lot of that kind of depends on the site conditions of where we're working. So in residential areas, particularly in water systems, about 400 to 500 feet. Put us out in the green space, maybe in a sanitary environment where we can fuse longer lengths of pipe, and we can go much longer than that.
Can CTPS handle vertical or horizontal bends, or is it only for straight runs of pipe?
No, great question. No, it's only for straight pipe. We can handle gentle deflections or maybe some kick deflections, things like that. But once you start getting to fittings and you start getting into 45s and 90s and things like that, those are, those are hard stops for us. We're going to make an excavation there, and we're going to use those areas as we lay out the job to put our access pits.
What limitations are there for upsizing 12-inch pipe to 18-inch?
Say again one more time. I'm sorry, Emily.
What limitations are there for upsizing 12-inch pipe to 18-inch?
Yeah, great question. So as you get larger in diameter and you start upsizing pipe, with us utilizing the existing alignment, we're kind of stuck at that sort of 20-inch max as far as pipe sizes. Maybe a little bit, maybe we can go one size larger. Once you start to upsize, there's just some dialogue that we want to have on what other existing utilities might be there. And so the more you upsize and the larger your pipe is, the closer in proximity that you may be going to existing utilities. And so when we use the existing alignment and we're at smaller diameters, and maybe when we're not upsizing, as far as the spectrum of safety goes, that's about as safe as it gets as far as using that alignment and not worrying about existing utilities. Even upsizing one, generally not much of a concern as far as what other underground utilities are there. Once you start getting into larger pipe, and then once you start upsizing even more, you start to just bring the other underground utilities into play. And then we want to have the conversation of like, what might those conflicts be? Is there other, are there other utilities in the area? Are there other, maybe sanitary lines, storm lines? Are there fiber optics? Is there something that's been kind of there that kind of might get in our way if we start, putting in that larger pipe or upsizing a little bit more? So it's just something to kind of talk about once we get into larger upsizes or bigger diameters as to what other underground utilities might be there.
What is the challenge of using this technology for gravity A pipe?
Yeah, so for gravity, the challenge runs into what do you want to do with your pipe that's there? So generally for gravity pipes from a cost-effective basis, a rehab technology like CIPP is probably the most cost-effective way to rehab that system and give you back a 50 to 100 year engineer design life asset. If you want to upsize that asset, then that's not an option, right? Or if you want that asbestos cement pipe out of the ground, then again, that's not an option too, because we're leaving that asset in the ground. So if you're not upsizing and you don't really care that you're leaving the asbestos cement there, and you just need a structural solution, then CTPS is probably not the way to go. Is it possible? 100%. Good, better, best. Is that the best thing to do? Probably not. Once you start to want to upsize, or you want that asbestos out of the ground, or both, you start bringing in the CTPS technology. The challenge there is that we're digging access pits, and we're doing that in a gravity system. And so usually when you're doing access pits in a gravity system, you've got manholes to contend with, or manways or access points to contend with. So you've got to deal with a fused pipe and the size of those access pits. Depth becomes a major issue for us, or a major factor for us. Shallow pipes tend to not be that big of a deal because our excavations tend to be a lot shorter because we're dealing with bend radiuses. When we start to deal with deeper gravity systems, we have to extend the length of our pits to accommodate for the bending radius of the materials. And if you're doing that, the pits can start to get a little long. And once you're dealing with manhole to manhole runs of say 300 feet, and you've got really long excavations to handle your bending radius on say a 12-foot deep or a 15-foot deep gravity manhole or gravity line, the benefits of going trenchless with CTPS start to kind of fade away. And that kind of becomes a little bit of a, more of an uphill battle for the efficiency and effectiveness of the technology as compared to other things like open cut.
Has CTPS been used in large-scale municipal projects successfully?
Yeah. The current project that we're on down in the city of Sunrise is a pretty sizable project. There's another one that's coming after that in a similar area, not as big of a project, but that one's about I think a 38,000 linear foot job. Most of that one was water. I think about 30,000 feet of that was water, and maybe 7 or 8 or so thousand feet was sanitary sewer force main. So the process, it sets up really well for large scale projects like that, because just like any technology, there's a lot of efficiencies to coming and setting up shop and just kind of grinding out footage day in and day out, right? The crews get into a rhythm. the inspectors in the city. Like it's just these large projects that just have a lot of footage. They're not overly complicated projects. They just have a lot of footage. They tend to go pretty well just because we really find our stride and we get some efficiencies. In comparison, those jobs, are a very different comparison to maybe a small, 1,500 foot or 2,000 foot job. Once you finish with that job, you've kind of hit your stride and you're ready to chew up more footage, and it's just the job's over. So on a 38 or 40,000 foot job, it's a pretty good one for economy of scale and for the efficiencies of the technology. So if there's anybody that's in the area that wants to go kind of take a look at the job or wants to do a site visit, it's an ongoing job that still has a little bit of time left on it. So it's a great opportunity for anybody that wants to, uh, make a site visit and take a field trip and go take a look at it. So my information is there. We're going to send a follow-up email. You'll get that from me. So if there's anything from a follow-up perspective, particularly involving that Sunrise job, please reach out to me and we can set up a time to get together.
Is there any ground cover required in the receiving pit to contain the AC containing bentonite clay?
Um, no, I'm trying to just make sure I understand the question. We're gonna dig the excavation in the receiving pit. I don't know if there's any ground cover considerations. Oftentimes, we will line the excavation depending on the site conditions. We do want to try to keep it dewatered if we can. We do have, weather to kind of work around. We're dealing with a cementitious type material. So making sure that we can uh, properly get that asbestos cement material out, that slurry out efficiently and effectively, is really important for us. And again, just like a lot of things, there's a variety of different ways we can kind of skin that cat. From the materials handling perspective, I kind of mentioned there's a few different steps that we can kind of take depending on what state we're working in, what municipal owner is there, what the material disposal company that we're working with wants to do and prefers. So there's a few different things that we kind of have to consider and do consider as we're doing the process, and requirements that we need to meet in the materials handling part of it. Hopefully that answers the question.
How does the cost of CTPS compare to full pipe replacement?
Yeah, great question. My favorite answer that I hate giving is it depends. Unfortunately, it kind of depends on what type of open cut replacement is doing. In general, CTPS tends to win out over open cut construction, but a lot of that depends on the site conditions and what's going on. Um, if you're directly replacing that new line and you're taking it out and you're replacing it right back in the exact same place, CTPS is going to be much more cost effective. If you're laying that new line across the street, or if you're having to reroute it and you're having to, maybe reconnect services in a different configuration, right? Now your long-sighted services or your short-sighted services, and your short-sighted or your long-sighted, that's a little bit more involved. So it kind of depends on what type of direct replacement that you're doing. If you're literally laying a new line right next to the old one and you don't have to put anybody on temporary water, you can just lay the new line and just kind of switch the line over. Sometimes that can be a little more cost effective than our process. A lot of this depends on how much footage you're talking about. So it tends to be very cost competitive with open cut construction. Most of the time it wins out. It tends to be, if people kind of want an economy of scale, it tends to live inside. So it's generally more expensive than pipe bursting of what, if you were going to pipe burst clay or pipe burst, metallic pipe or something like that. We have to deal with materials handling, right? We've got drilling mud to deal with. We've got material handling from the slurry to deal with. So we've got those additional added costs. So it's comparable, but with those additional added costs there. So it tends to fall in between those two. Generally a little more cost effective than open cut, but to be honest, not always, right? We don't always win out. Where we do tend to win is in the restoration and in the social disruption and the efficiency and speed with which we can do these projects in comparison to what the open cut methods would do. That speaks volumes to a lot of different municipal owners and engineers who would rather have their residents disrupted for a few days versus a few weeks as you compare open cut to CTPS.
Are there any concerns with making repairs or tapping the new replaced pipe in the future?
No, it's a brand new pipe. So depending on the pipe material, particularly if it's fusible PVC, you're dealing with a PVC pipe. So future repairs, like even just making the reconnections as we lay the new line, those fittings and those materials are off the shelf AWWA fittings. So the process as far as future repairs or even just making even the current connections with the materials tends to be a lot easier just because you're using AWWA fittings that are PVC fittings. So there's a lot of convenience, particularly when you're dealing with fused and fusible PVC.
What is typical install or production rates for the CTPS process?
Yeah, great question. So again, kind of, we sort of touched on this, depending on where we're working and, is it heavy residential or are we out in kind of a green space? We're usually doing between 400 feet and 500 feet in a day. So there's a little bit of setup activities that kind of come before that, right? Remember we said we've got to disconnect our services. We've got to take those residents off of their connections and put them on a temporary water system. But as far as the actual CTPS process goes, we're doing, and in that graphic I showed that kind of had the one typical setup with the red call out box around it, we're doing, and that was half a block, we're doing one of those a day. So in that particular neighborhood, we would do that one, run on one day. And then we would go ahead and jump to the other side of the block and we would do the other half of that block in another day. So as far as the CTPS process goes, we would do that entire block about 1,000 feet in a 2-day time span. But again, with a little bit of setup and reconnection on either side of it. So great question. That's generally what we're getting. Safe answer is about 400 to 500 feet. So Emily, I'm not sure how many more questions we have. I know we're kind of running up on time and I really want to make sure we're cognizant of everybody's day and schedule. If there's additional questions, I know we've got them logged. I'm happy to follow up with everybody individually with some of the stuff that maybe I didn't get a chance to answer. I know there's a lot of questions around the process because it's, in my opinion, it's quite innovative. There's a huge need for it. Please look for a follow-up email from me. I'll have a lot of the resources that we discussed during the presentation. Obviously, my information is there on the screen, but you'll have an email directly from me that you can reply to in a couple of days if you've got further questions or if I just ran out of time to get to what you had asked today. I really appreciate you guys joining us today and taking a little bit of time out to learn about a really neat new process.
And as we bring today's ASCE sponsored webinar to a close, I want to extend our sincerest gratitude to Azuria Water Solutions for sponsoring this informative session. And of course, a huge thank you to our speaker, Andrew Costa, for sharing his expertise and valuable insights. Thank you all for attending today, and we hope you found this webinar valuable. The recording will be available on demand within 48 hours, and all those registered will receive an email, letting you know when you can view it. Everybody, please be safe and be well. Goodbye.
Thank you.